Hello everyone and welcome to today's webinar, CANSO and Fly AI webinar. And that is AI in ATM, enablers and use cases. Before we get started, I'd like to go over a few items so you know how to participate in today's event. You may have joined the presentation listening using your computer speaker system by default. If you prefer to join over the telephone, just select phone call in the audio pane and the dial-in information will be displayed. You'll have the opportunity to submit text questions to today's presenters by typing your questions into the questions pane of the control panel. You may send in your questions at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation. It is my pleasure to introduce you to our moderator today, Patrick Sauchu. Patrick is working for DSNA, the French air navigation service provider, as Program Director. He is managing the DSNA contribution to CESAR, which includes more than 50 R&D and deployment projects. He is a member of the Eurocade Council and he is currently chairing the CANSO Strategic Technology Workgroup. Patrick, I hand the floor to you.
Thank you, Hélène, and welcome everybody in this Fly AI webinars organized by CANSO. Good afternoon, good morning, or good night for some of you. I know you are many around the web. Today, the seminar is called Enablers and Use Case for Artificial Intelligence. And as chairman of the Strategic Technology Working Group, I have the pleasure to be your moderator today. So next slide. So this seminar is organized by CANSO and it's part of a series of 7 AI webinars organized by Eurocontrol. Next slide, please. So the 2 first webinars have been very successful. I'm sure you will continue to learn a lot about artificial intelligence in this webinar. I know we are about 1,000 people registered for this seminar, and I wish you a good webinar. I'd like also to thank Eurocontrol for giving CANSO the opportunity to be part of this series of seminars. Next slide. First, I'd like to give you a few words about the CANSO Strategic Technology Work Group. So this is a work group that was established in September 2019. Today composed of 28 members from various organizations, NSPs, industry, service providers, and the main objective and the final objective of this work group is to provide input into a coordinated work plan for CANSO Standing Committee and regional working groups, dealing with particular aspects of technological deployment and implementation planning. To achieve this objective, we have 2 intermediate steps. The first one is already achieved. It is to produce an overview of the current state of technology deployment and implementation planning of various technologies at regional and global level. We have proceeded with 2 workshops before the COVID crisis, and then after the COVID crisis, we have proceeded with surveys, and we have now, I think, this overview as an input for our final goal. The second step that is going on is to undertake an assessment of the potential impact of new technologies on NSPs and ATM performance. Next slide. For this second step, we have selected 7 new technologies that we considered as having a significant strategic impact on ATM business. For each of these technologies, we have created an expert team made of experts in these areas, in order to develop 7 white papers. So these 7 topics are virtualization, blockchain, new concepts stemming from UTM, airborne capabilities, system-wide information management, SWIM, space-based CNS, and artificial intelligence. And why we are presenting you today this is because the first white paper on artificial intelligence is almost ready for publication. It will be published this month. So I'd like to thank the team who has developed this white paper, and especially the team leader, Béatrice Pesquet. This leads me to the presentation of the panel list. Next slide. Thank you. So today our panel list will be Béatrice Pesquet-Popescu, who is working for Thales as Director, Research and Innovation Director, implementing artificial intelligence strategy. She is also co-chair of the EuroCAE Working Group 114, dealing with artificial intelligence, of course, and our team leader for this white paper. Then Zoltán Molnár from Ungerl Control, who is a safety and risk management expert, will address these important issues that are safety challenges for artificial intelligence in ATM. Then Eduardo Garcia, who is manager of European ATM coordination and safety, will present as human-machine collaboration in artificial intelligence. And Eduardo is coordinating most of the European positions, CANSO positions, on technical, operational, and safety aspects. Then Firdu Bhatti, who is manager of a team for analytics and new entrants for the FAA. He is involved in many projects involving risk analysis, risk modeling, and machine learning. And finally, Michael Poiger from Frequentis, who is a senior lead expert of control room for control room, and is an expert in human performance and user expertise. So now I hand over to Béatrice that will present the outline of this webinar and of the white papers. And I remind you that there will be some questions at the end of this question and answers at the end of after the presentation. Thank you. Béatrice, the floor is yours.
Thank you very much, Patrick. Good morning, good afternoon, everybody. So first of all, I would like to thank all my colleagues who contributed to this white paper, and some of them, you will see them today in the webinar. And of course, to invite you to download the white paper as soon as it is available. So next slide, please. The way we organized the white paper and also the webinar is by first putting some enablers and then illustrating with some use cases. So first of all was the infrastructure for exchanging data, why the explainability is important for AI, how the certification comes into play, and of course, what are the safety considerations to take into account. Last but not least, it is very important for us to see how the human-machine collaboration will contribute to the success of this technology. And then we have some use cases putting into practice these considerations. We shall present you today some examples of how to increase safety using AI, how to give the controller some advisories for conflict resolution, and the voice recognition application for ATM. However, in the white paper, you will find also much more examples, including demand prediction, optimal sectorization, remote hours, and much more. So without waiting anymore, let's talk about the first enabler, which is the necessary infrastructure data. So next slide, please. So as you know, indeed, the strength of artificial intelligence relies on the availability of a huge amount of structured and unstructured data that typically converge to a infrastructure, a common infrastructure, generally a data lake. But these data become interesting when they are available, and in this context, availability must be defined as per two main axes. First of all, the access to data, and then the trust you have in the data, defined by the famous CAA model: confidentiality, integrity, availability. Other properties of interest are, of course, the need for interoperability and the need for traceability, which leads in turn again to the trust in the data that the different stakeholders are exchanging. And it must be emphasized that even if there are different initiatives around the globe for providing platforms for ATM-driven data, the approach still seems to be fragmentary. And well, here you have listed a number of initiatives, some of them stemming from collaborative projects like Data for Safety, Data Beacon, others from institutions with international or large regional footprints like Eurocontrol, FAA, IATA, ICAO. But we also see taking form a more advanced form of data governance, like in the Gaia-X project, which is initiated by Europe and is aimed for developing common requirements for a European infrastructure providing data and services in an open and transparent trusting environment. And this trustworthiness is related to the data exchanges. Data exchanges are a fundamental pillar for AI to become reality. And another pillar for achieving it is the explainability of the algorithm. Because we talk here about data-based AI, so basically machine learning. And this allows me to go to the next topic, which is the explainability. Next slide, please. Indeed, one of the pillars of the AI trustworthiness is the explainability. Because us as humans, we need to formulate the reason why something works or does not work well. And this amounts, actually, the problem amounts to the black box issue of the neural networks. Because we all know that when we want to formulate the requirements for such kind of systems, looking into the model description at software level does not help you to understand how it behaves, contrary to the rule-based or model-based software. And the problem is even more difficult because the data-based methods look for correlation to exploiting data and not causality. And explainability actually needs causality. And a very classical example is that you have on the slide is the number of Nobel Prizes, which is strongly correlated at nation level with the chocolate consumption. This is clearly a correlation that can be easily inferred from basic data, but in no way it seems that this is a useful causality. It's not useful, and therefore it will not be appropriate for serving as an explanation for how would function a predictor of future economy success fueled by chocolate consumption. And another very representative example is the one with the husky classified as a wolf. Here, the explanatory system in itself is based also on a neural network, and the design in the classical paper from where I took this example indicates that the feature leading to the classification of this image as a wolf is the white nose, which is definitely a bad feature to make the difference between a husky and a wolf. And very bad for providing a meaningful explanation. So this shows you very clearly the difficulty of the problem, and is also related to another issue we need to take attention when we are using such kind of systems, which is the possible biases in the data, because here actually the images containing wolves containing also some snow. So all the challenges related to the machine learning, the difficulty to make a meaningful specification, the data representativeness, the verification properties, and the explainability are all actually strongly related to each other. And it's difficult to detect, for example, here the bias in the data till you don't see it reflected on another property, here the explainability. but it could have been the robustness or any other feature. So next slide, please. Another dimension in the explainability is also the human factor, because several user groups exist in ATM with different expectations for different explanations. And this is actually a common issue for all the safety or business critical industries that want to have explainability as a feature for their system based on AI. For example, the data scientist or the end user, be it pilot or controller, the regulation authorities, they all have different knowledges and different mental models. So they expect explanation for different reasons. The end user will need an almost real-time explanation, which is very quick in time and very pertinent to help him in the decision. The data scientist will need a thorough insight into internal features in order to improve the model, while the accident investigator will need a full file of evidence of the system, but not in real time. So another important feature for the explainability, I would say, is also to know its own limits. This may seem very philosophical, but it's very important for the safety critical applications in ATM, because the system needs to operate only under the situations where it has enough confidence in its own output. And this brings me to the next slide, please. So the explainability is also related to other aspects in the development process, like the learning assurance, because during the development process, you may extract some low-level or high-level features that will help both explainability and learning assurance. And you may also need to store them for traceability and proof in front of the authorities. So the human factor comes to all these HMIs that provide the explanation, and they need to be different also for the different user groups. And this shows also the link to the operational monitoring, because the alerting processes will definitely give indications for explaining anomalies in the functioning of the system, but it is definitely related also to the data management process, since the data that leads to these behaviors needs to be traced back to the root cause, and for this you need to store during the runtime, and also to think about the coherent architecture. So this brings me to the system consideration. And this is a good transition to introduce the certification aspect of the AI in avionics systems. So next slide, please. So next one, yes. I will talk to you about the EuroCAE WG114 SAE G34 common group. This is a group jointly created in June 2019 in order to coordinate the standard creation for AI certification in aviation and provide the guidelines about certification activities related to safety critical products, including AI modules. So the scope of the standard is to provide guidance for the certification of aeronautical products, so both for airborne and ground systems, both manned and unmanned. And as I said, it's a joint effort between EuroCAE and SAE. It gathers together more than 500 engineers and practitioners all over the world. And all these people represent the main component system manufacturers, the UAS manufacturers, but also the regulators, authorities, NSPs, airlines. So, well, I would like, first of all, to thank all the contributors to the standards for all their efforts, and to present you a little bit what are the outcomes. The house on the, no, please remain on the previous. So the house on the right-hand side actually shows you the way this joint group has started and its aim. First of all, the stakeholders discussed and agreed upon a number of concerns the taxonomy, which needs to be common across the different fields. And all this was set it out by discussing a number of use cases in avionics with their specific concerns. These are the foundations of the house, and this structures the entire work. And the main output will be a standard with the two main applications, as I said, airborne and ground. It is not yet settled, but in the past, these two domains had differences that led to parallel yet similar standards. And we'll see if this distinction will still be needed for this standard. And actually, the work is organized in subgroups, coordinated by a common leadership team. So next slide, please. So you have here actually the global roadmap for the standard and associated outputs, ER and R documents. So you have the taxonomy and the statement of concerns, the use cases as associated documents. And the first version of the standard by the end of 2022, a second version by 2024, including probably, so in the first version we have offline learning. In the second version we'll probably have online learning and other AI technologies more than neural networks. And you see in the bottom of this slide actually also the roadmap from EASA that provides actually the three levels of guidance for machine learning. And you see that the two roadmaps are quite well synchronized. And this is very good because EASA, for example, in Europe provides high-level guidance, and the standard will be more precise on the means of compliance that will be implemented. And as you know, the role of all these standardization efforts is to bring safety into systems, including AI. And now I will let my colleague Zoltan to present you the safety considerations for AI.
Hello, good afternoon, everyone from Budapest. Today I would like to show you the safety aspects of AI and machine learning and the differences between traditional software safety and AI and MS safety. The next slide, please. So traditional software safety is based on existing standards. The industry has quite great experience in safety assurance of this type of products. There are several standards like AD153 and AD109A, and the basic methodology is to identify the potential effect of a software failure, the severity and the likelihood of this effect. And for example, if we are using AD153, then we can identify the software assurance level of this kind of software. And based on that, the standards let us know the most important steps which should be followed to guarantee the safe software assurance level and that the software will work as it's expected. It won't do less, but won't do more. For these, there are important assumptions. The first one is that the algorithm should be fully explainable, traceability of the requirements should be provided, and fulfillment of these requirements should be justified. The next slide, please. On the other hand, in case of machine learning and AI, there is an algorithm, but the algorithm and the data form together the machine learning models. The model is trained on the data, and it will identify patterns based on the data. As Beatrice said in the last presentation, black box and explainability issues are a big concern in machine learning safety. Decisions can be based on unexplainable patterns, and this is a critical aspect from safety point of view. The data is another challenge because the performance of ML algorithms and the ML models is highly dependent on data itself. Training, test, and validation data sets should be safe and should be compact to provide safe machine learning. And there is another aspect, is learning process, which can be the subject of bias or variance, which can cause overfitting and underfitting. Overfitting means that the model is too specialized for the training data set. It cannot generalize. On the other hand, underfitting means that it's too general. Both should be avoided to provide a good performance. These challenges are mainly for the supervised learning. Reinforcement learning is safety of reinforcement learning is another topic, and it's still ongoing research. The next slide, please. So what can we do to solve these problems? At first, in scoping and requirement definition level, we have to define what we expect from the system and how critical is the application. Here, SWAL-like matrices can help us, classification schemes can help us to identify the safety criticality of an application. The next step is data selection and preparation. The data set safety of the data sets should be assured. These data sets should be correct and complete for non-nominal scenarios too. So this should be representative. Representativeness is a key factor because in this case, the software or the machine learning model should work in case of non-nominal, rare, even non-normal scenarios, not just in the normal ones, to have a robust and safe system. Of course, the size of the data is also the size of the data set is also a very important question. And the quality of the data set, we have to take into consideration cybersecurity aspects too. Data assurance level, the concept of data assurance level can be helpful here. Next step is the model selection. We have to choose models which are more explainable, although this is quite often a trade-off with performance. And explainable AI techniques also can support us. It's again an ongoing research, but it's quite promising. And with formal methods, it can help to describe or can explain even machine learning models like deep neural network, which has a big part of black box. Next step is training assurance. Hyperparameter tuning and loss function optimization can be a solution here to somehow integrate the safety aspects, and verification and validation, of course, to match with predefined acceptability parameters, but validation should be conducted in various levels of abstraction of the system, in component, subsystem, and functional system level, because in the end, we will integrate the machine learning components to our functional system. There are other solutions like have more machine learning component for the same task and apply some kind of voting logic for that, or to have a machine learning component and a non-machine learning component for the same task to enhance safety, as it happens in other industries. The next slide, please. Thank you. And which is very important is the question of safety and resilience. as the good performance and better and better performance in machine learning can accelerate the automation of ATM, we have more and more issues, and the human-machine interaction, human-machine interface is a very important question which should be assessed, and Eduardo will speak about this in the next presentation. It's really a key topic. Of course, we have to keep our system, we have to keep the resilience of our system, of this new functional system. And for that, it's very important to know our functional system. It's more important maybe than ever before to identify the bottlenecks, identify the strengths and weaknesses, and see where machine learning and automation can really give added value. So where really can add value to the system, and see where not. So we have already started this work in ANSP level to identify how automation and machine learning can support our functional system, what are the boundaries of it, but I think it's a work which should be done in an industrial level, and that's why it's very good to have this kind of forums where we could discuss this kind of questions. Thank you very much for your attention.
Thank you, Zoltan. Hello, everyone from Brussels. It is my pleasure now to introduce the fifth enabler, human-machine collaboration. So when it comes to artificial intelligence, human-machine collaboration is of paramount importance. It is strongly linked to the previously mentioned issues of trust, explicability, and safety. In CANSO, we foresee a fluid cooperation framework between human and AI to minimize operational risk and improve the overall performance of the ATM system. Experience gained during the successful implementation of automation in the cockpit or in the human traffic management world can be used in designing automation in ATM systems. In a human-machine collaboration paradigm, the human roles are developed and implemented in a way that fosters trust and confidence by the human in the automation functions. The AI is not used as a simple tool, but it is used to complement and augment human capabilities. The objective is that a human expert can focus in areas where additional operational perspective is needed, while the machine can automate a large and repetitive task that it can handle more accurately in a scalable fashion. So, for instance, AI models can be used for information acquisition and analysis in order to enhance situational awareness and monitoring, and also provide decision support to increase efficiency by enabling human experts to focus on more complex decisions and tasks. I would like to stress that it is key that trust in the human-machine system is improved by upskilling human operators to better understand the new database algorithms paradigm and adjust their expectations to the system limits. So we move to the next slide. In the current AI machine learning application, the role of human does not change significantly. However, the introduction of AI models will support higher levels of automation, more advanced decision-making tasks, and there is little doubt that it will impact the way work is performed in the future. The roles and responsibilities of human in the functional system will change, evolve. There could be new actor, young human-machine system working with different look-ahead time horizon, aerospace scopes, and operational performance indicators from the ones that exist today. One key message that I would like to stress is that it is of paramount importance to keep the human in the loop. This is essential in a synergic human-machine collaboration and contribute to the resilience of the functional system. Air traffic controllers, for example, should always be able to override some procedures in a given context while still maintainable and acceptable level of safety. It is even more important because application increasing the level of automation to support ATCOs to handle traffic with higher complexity might decrease situational awareness. Proper assessment of this issue is important to make the ATCOs self-confidence in their new role. Again, explainability of AI is a key factor to build trust and support human-machine collaboration. It is now time to know more about a number of examples where AI has been successfully implemented in ATM and with its use shows the potential to deliver real benefits. So it's my pleasure to give the floor to my colleague, Dr. Fir Dubati from the FAA.
Thank you, Eduardo. So if you go to the next slide, I'll be speaking about the safety application. Earlier, Zoltan talked about AI safety, and I'm speaking about safety as well. There are two different aspects of safety. What Zoltan talked about is safety assurance that the AI needs to manifest. And I am speaking about the application of AI for safety management system in ATM environment. So in general, there are two categories of application for AI in the safety domain. One is to automate some repetitive tasks or activities to enhance efficiency in the way we manage those repetitive tasks. The other one is risk detection or event detection. Now, there is some overlap between the two, but in general, those are the two categories. Now, I'll be speaking about this four application area. We selected, there could be many other applications of AI, as you can imagine, but these are selected based on information and experience in deploying in practical application. So I will speak about key performance indicator, how AI can enable developing and managing a monitoring system using key performance indicators. And a related topic to that is a comprehensive aggregate risk matrix where you combine multiple KPIs to measure the safety performance of this system. And another important aspect of safety management system is event categorization, that you have to analyze how severe things are. And that could be automated to large extent using automation driven by AI. And another aspect is anomaly detection that is potentially could be a game changer for future risk detection. If you go to the next slide, please. So to different extent, pretty much every navigation service provider will have to do some kind of key performance indicator to evaluate the safety performance of their system, right? And one key to achieve that is understanding, collecting data from end users and people on the field, from controllers and pilots. And the main vehicle for that, at least in the US for the last 30 years, through manual reporting. So you encourage controllers and pilots, the system users, to provide safety relevant information so that the people who manage the system can have a better understanding and mitigate the risk. So that is the main system, and it's been working for some time, I think for more than 3 decades now. And recently, another application where we can enhance the data collection process by having rule-based deterministic algorithm to detect the different KPIs. The kind of KPIs that I'm talking, I have some examples here, but there are other dozens of these. For instance, in the surface environment, in the airport environment, you have Class B excursion, runway. No, Class B excursion is airborne actually. Runway overruns, rejected takeoffs, unstable approaches, approach overshoot. And like I said, there are a lot more. These are examples. So these are individual metrics, key performance indicator to measure how you are performing in the particular dimension of the system. Now, we've been doing this for years and years. So we have the knowledge base. We have sufficiently large data to automate a large aspect of these processes by training machine learning algorithms. Now, some of the advantages of machine learning is it's a scalable solution. As the system changes over time, the machine can easily adapt to that change in size. And they are also a stable detection mechanism because they are consistent. So assuming that you have large enough data to automate or to train a machine learning model, then the future application of that AI is consistent in the sense that that logic is embedded in the AI, is not explicitly told, but rather trained from existing knowledge. So, so that is another advantage of having machine learning do this kind of stuff. Now, we haven't done much in this area, although recently, FAA partnering with Wider, we have applied a voice data, leverage voice data to train machine learning for detecting US encounter with manned aircraft, and the accuracy of that model is very, very good, acceptable, better than some of the rule-based engine that we have, and also even better than the human categorization. So this is one application area where you can measure individual key performance indicators to different parts of the system. Next slide, please. Right, so this is not unrelated to the first one. This is aggregate. So what I talked about in the previous slide was these are individual things you measure, right? Very specific to that procedure, to that environment. But at the end of the day, you measure the performance system aggregate fashion, right? You need to measure the performance of the system at a larger scale, which means you have to combine some of the key performance indicators that you measure independently. You have to combine them. Now, in some cases, that means you have to look at different level of events, could include accidents as well, right? So in general, the extent might be different, but this is a complex system, right? In the US, we have a very complex national aircraft system where different procedures, rules, technology that generate different, potentially lead to different risk level. So the way to measure the overall performance of the system, or at least part of the system, is to take into account all these individual key performance indicators. Could be accidents, incidents, and you have to combine them in a way that you can measure the overall performance. In a way, it gives you a risk index of the system. And the advantage of that is you can measure the performance, you can actually trend it into the performance system over time as well, or in any given period of time. But what is required to do that is quite involved. Without automation, particularly using machine learning, it is very difficult to do that because you have to tap into multiple data sources. You have to identify the type of events that are relevant to the part of the system that you want to measure the performance of. And then you have to assign relative weight to each and every outcome, events and accidents, and if there are injuries and property damage, then you have to take into consideration. So that process is nearly impossible to do manually. So automation is the key to make that happen. We do have experience in the US NASA. We have actually in the air traffic organization, we have deployed 2 metric systems supported by AI, one for the surface environment, one for airborne environment. Now, like I said, they tap into multiple data sources and identify relevant type of events for both environment, and they assign relevant weights, and then gives you aggregate measure. And that gives you some transparency and a high level aggregate measure so that you can communicate to all stakeholders and the general public. So that's another application where AI can enable this kind of measuring performance of the system. If you go to the next slide, please. Here is where earlier I said that in general there are 2 categories, right? One is to automate repetitive tasks, another one is risk identification. Now you can categorize, now the 2 are not unrelated, there is some overlap. But this one, so the example that I gave for this particular application is, so you collect, one of the key requirements in SMS is to collect information, all right, potential events, and then identify them, analyze them, understand them, and categorize them according to their severity. One of the mature systems that we have had for more than 2 decades is runway incursion categorization system. I think this is, in fact, a requirement from ICAO that every service provider need to analyze and categorize each runway incursion. And there are some simple rules to by which you can categorize these events into category A, B, C, and D. In general, A's are more serious events, B are the next series, C and D. Now, we have, in the US, we have set of experts that are dedicated to analyze this data. They come in and categorize them. But we have been doing this for some time, and we have accumulated a large amount of data, large enough to train machine learning, at least to automate a large portion of this process. So the thinking behind this is, if you can train a model that can categorize, like, let's say, the less severe event with accuracy high enough, then the human expert can focus on things that are more critical and things that require more attention, like the category A's and category B's. And again, this is also another area we have actually demonstrated by, we were able to train model using the data we have collected over more than 2 decades now. And we have demonstrated that the category A, B, C can be completely done by the machine, and people can focus on the most serious ones. And so this is, in a way, you can categorize this as a kind of, making the repetitive task is more efficient, so that people no longer need to read this. Okay, next slide, please. So this is anomaly detection. This is one kind of newer. Now, pretty much everything that I have spoken about until this point is on supervised learning. Supervised learning in general means you have annotated data, you know exactly the kind of target that you want to predict or classify. But it's not every area of the system has sufficient annotated data, right? So that means you need to do some kind of anomaly detection. Anomaly detection is nothing but you look through a large amount of data and try to find behavior that's peculiar, that's different from the majority of the cases. And potentially that could be a small subset of the data that you need to pay attention to. Because I guess, primarily because the aviation system in general is very safe system. So this is, in a way, is rare event detection, because the risk in the system is so small, human can possibly go through every single flight in a given system, try to identify which one is a risky behavior. So anomaly detection actually can do that, because, like I said, ML is scalable. You can actually go through the entire flights in a given day or in a given week. And then the machine can identify a small segment of the flights, a small portion of flight that have potential risk. Then human experts can actually look at it as a very small subset and validate whether they're truly risky behavior. In the US, NASA has demonstrated this using one class support vector machine, and they enhance it using their own kernel method. But for this example, I'm showing one from a paper titled Detecting Flight Trajectory Anomalies and Predicting Diversion in Flight Transportation. So what they did is they also used a simple one class support vector machine. So the machine was not told about anything about the flight plan. It didn't know the trajectory. So this one right here, the upper right corner shows that a flight from Munich to London. So, and without any anomaly, right? So you see the track. Now, what they trained is just by using parameters like position, velocity, and altitude of the aircraft, they were able to detect if there is a diversion in that flight. And in the second case, in the lower left corner, you see that they were able to detect the diversion of that flight back to its original airport way before it arrived at the original airport, using simple parameters like, to say, position, velocity, and altitude of the aircraft. So again, this is a simpler application, but you can see the potential of anomaly detection because we don't have a large amount of data in every part of the system that are annotated. So another potential application in unsupervised learning is actually you can have the output of unsupervised learning to help you come up with supervised data in the future. But this is, like I said, that has been applied in some areas, but there is a lot of potential in applying anomaly detection. With that, I'll hand back to Beatrice. She's going to talk about the conflict resolution.
Yes, thank you, Firdu. So I will present now the use case, another use case, which is related actually to increased automation and the digital assistance to the air traffic controllers. Because indeed, in future products, and for Thales this is the Top Sky ATC1, we will integrate all the necessary steps to an increased level of automation by advising users on usual situations, and in other cases, we'll integrate AI for supervision and maintenance of the system. So, for instance, here you have the feature called conflict detection and resolution, CDR, which is a real answer to many NSPs that express the need for increased efficiency for their air traffic controllers. So behind the usual conflict detection system, which is performed for 20 years in our system, Top Sky ATC1 will advise controllers on the resolution of conflicts by choosing the best trajectory, considering also environmental impact, considering safety. And with a single click, the controllers will apply the change to the system if they want to accept it, and send it automatically by data link to the pilot. So next slide, please. First I will show you a video that explains how the feature works and presents a testimony of some controllers that tried it during the Cesar sessions, where we did some experiments with the Coupang controllers, and you will see that the controllers love it. So please launch the video.
In the scope of the CESAR 2020 program, thanks to a Thales platform, some cool plans controllers have experimented neo separation tools, allowing to introduce some level of automation in the process of aircraft conflict resolution. On the working position, the system automatically informs the controller that a conflict is detected and a resolution proposal is available. The controller displays the computed resolution proposal generated by the system in order to not create another critical conflict in the future. In the current case, the controller accepts the resolution proposal, which triggers the flight plan update. The conflict disappears from the track label and from the conflict window. The separation tool is displayed for helping the controller to monitor how the resolution clearance is applied.
It was to examine the viability of using system-generated solutions to conflicts that controllers would come across on a day-to-day basis in the operational environment, and see how we could actually introduce them into the future. Well, what we did for this validation was we compared reference scenarios that we'd actually come across on day-to-day in real-life working environments, and compare that then to scenarios where we'd have the solutions included. And yeah, we have plenty of data now that we can analyze at the end of the validation.
technical objective was to build a viable prototype in order to validate the introduction of automation in the conflict resolution process. During 1 year and in close collaboration with our COPANS partners, we capture the way the controllers are managing and fixing the aircraft conflicts. And we use this picture to develop our resolution tool with some artificial intelligence inside.
And the initial findings are really positive. I think this project has the potential to be groundbreaking. And I think we've really started on a really solid foundation that we can build on into the future. And I can see this actually being of real operational benefit.
Okay, so thank you. So, now if we come back to this digital assistant, actually, you see that the AI is a key element in the roadmap for this digital assistant. And as Eduardo explained, it keeps the human in the loop, and it integrates advisory in a globally safe architecture. Many other advisories will be hand-raised, and artificial intelligence will help more and more by recognizing traffic situations, as also Firdo explained, and applying the right solution. So this is the future, and you know maybe that Eurocontrol predicted a full automation of air traffic control in 25 or 30 years from now on, and therefore these tools are definitely considered as necessary steps. So this brings us to more complete digital outcomes, and this includes voice recognition, and I will let the floor to my colleague Michael to explain this to you. Thank you.
So thanks, Beatrice. Now I would like to give you a short overview about voice recognition, as Beatrice was saying, and how artificial intelligence could support it. Please go to the next slide. Great, thanks. First of all, I would like to start with the definition, because there were a lot of different words around voice recognition, speech recognition. So this means voice recognition is the overall term, and this can be separated in 3 areas. Speech recognition, the ability to transcribe words and sentences. The next one is language identification, ability to identify spoken languages. This is very interesting if you have a setup where you have different languages available, for example, English and German or English and French, for example. And speaker recognition, identifying the speaker. This is normally used for biometric identification. Today, I would like to concentrate on speech recognition, because there we have seen in the last years a big trend with the support of artificial intelligence based on training the speech model, interpretation of context, and also for the automation support. What I would also like to say here is we see, especially in the consumer market, growing up the speech recognition, and this was also mainly coming with the AI support. Please, can you go to the next slide, please? But what I would like to go here is, as Sultan and Eduardo was saying, yeah, it really depends where you want to use it. Yeah, speech recognition is not a technology which you can say, okay, I use it there and I use it there. We really have to think, does it make sense to train and well integrate it, because it has to fit into the overall process. So therefore, it's really in the first stage important to analyze where are the use cases and where are the improvement points. Saying this, it's also important due to the accuracy of speech recognition. For example, you have not always 100%, to find the right point where to integrate it in the process and also in the user interface, and which stakeholders are involved. To allow this, it's important to, first of all, identify the measurements, what you want to achieve with it, capture the overall process, and then really checking the points for automation, for the improvement points. This also helps you to investigate, is the effort worth the benefit? Yeah, because the problem is sometimes it's more effort to train to find the right information than the automation would bring from the benefit. And then you have a good baseline to implement the change and to have a next step for automation support. Please, can you go to the next slide? This leads me to areas of speech recognition. As I said before, it's not a way that we can say, okay, it's only for this aspect or for this aspect. So I split it up in 3 areas. The one is the assistance, for example, for the controller. This helps to increase operational effectiveness and reducing the workload. This is, for example, done for form fill-in. Take, for example, if the ATCO is speaking a clearance, the information can already be taken out from the voice and input into the system. And when he have the readback, he can confirm it. Additionally, command and control following impact as inputs what the controller was saying. The second thing is the safety, increasing system accuracy and predictability. And here, it's very important to highlight a lot of information is going over the voice stream. Yeah, so this means if you have analyzed this information and make it readable for the machine, you can easily do attention triggers, highlighting information, or making safety nets for conformance monitoring. The third part is the digitalization, and this helps really as a step for automation. You can correlate conversations, you can correlate other informations with it, and therefore it's a good baseline for automation. A good example, what I always see, is the simulators, because speech recognition is already used there to help reducing the effort of pseudo-pilots, because the language can be processed from the ATCO and then automatic answers can be provided. Please, can you go to the next slide? So we know it all from the consumer market, and it's already everywhere available. But why is not in ATM? The clear answer is we have different aspects to be addressed due to the nature of a safety critical control room. And what also Zoltan was saying, yeah, we really have to think what are the safety cases and how you can bring the human and the machine into a symbiosis. So what challenges do we have? The first challenge is with the recognition rate. Yeah, here we have never 100%. So how can we deal with it that we have not 100% recognition rate? So this must be in an intelligent way to be integrated. The second thing is the error rate, and this is really a big topic where you have to be concentrating on to limit it to a minimum, because otherwise it disrupts the operator, increases the workload. Imagine if you have safety net alerts, yeah, which pop all the time and they are not correct. Yeah, it's disrupting you, and therefore it really has to be minimized, and it can also lead to safety aspects. The third point is, and this is really something also for ATM specific, is the audio quality. So we have here technology from the pilot conversation, pilot to ATCO, ATCO to pilot, where we have limited bandwidth and therefore poor audio quality, and it's already hard to understand for a human what the meaning is sometimes. So therefore it's really a topic also for speech recognition to identify it in a correct way. And the last point is, and not underestimated, the availability of training data. In the consumer market, you have a wide area of data you can use for training the systems, training the AI algorithms, and processing it. Yeah, but this case we don't have in ATM because we need, for example, training data which are transcribed. Please go to the next slide. This brings me, how can AI support to tackle these challenges? So the first thing is, due to machine learning and due to the well-integrated systems into providing information, it helps with machine learning and AI algorithms to improve the speech recognition rates to a maximum. Yeah, for example, we are already on an article level at 95 or higher percentage. Clearly, the pilot conversation is a more challenging topic because of the audio quality. Then we have the minimize errors, and here we are also a step further with artificial intelligence. Due to the understanding of the context, it's very important to minimize errors, and therefore it has to be understood what is the context around, so you can prevent errors. Yeah, and there, natural language processing, natural language understanding helps to reduce these errors, and this can also help based on the contextual information. The third point is the audio quality, especially the pilot conversation, I have to say, is improvement of the audio quality. This is a big topic, and this can be also done with algorithms and pattern recognition to improve the recognition rate in these audio streams with the low bandwidth. And last point is, as I mentioned before, the availability of training data. And here, AI really brings a benefit because you need less data to train the systems, and therefore it can be more easily adapted to the ATM aspects and the ATM specialities and standards. Please, can you go to the next slide? So it was really a short overview, and therefore I would like to highlight some research aspects which are ongoing in the ATM area. So first of all, I would like to highlight the paper from the CANSO Strategic Technology Workgroup, as already mentioned, for artificial intelligence enabled and use case. And therefore also would like to thank the whole team for this paper, and especially my colleague Edward Gringinger. And then I would like to highlight two research projects or programs, say this way. The one is in CESAR, where several projects are addressing automatic speech recognition for article support. There was also a webinar before from Hartmut Helmke. And an Austrian research project where Frequentis and Ondeo is working, focusing on AI with automation of communication, monitoring of situation, corrective measurements for this necessary information. And additionally, I would like to highlight some other papers so that you get more insights in this very exciting topic of speech recognition. So thanks a lot for your attention, and now I would like to hand over to Patrick.
Thank you, Michael, and thank you all the panelists for this very interesting presentation. Now we have about 20 minutes for questions. I'm looking at the questions in the question window. I would say there are three types of questions. There are some questions about process, some questions about human-machine collaboration, and some questions about safety. And often human-machine collaboration and safety are very linked. I propose to start with the questions about process. There is one question that is, who ANSP industry academia should be taking the lead in researching into potential use case of artificial intelligence? Who would like to answer? Maybe Beatrice, Eduardo, Firdu?
Oh, I can give a first short answer. I would say that the three of them have to work hand in hand, because actually the real use cases come from practitioners, from ATC controllers, and actually there is an industry working to solve them, but there are, as you have seen during this webinar, a lot of tough questions, and here the academia can bring a real help and can solve tough questions. So what I have to say.
Okay, thank you. Nothing to add from the other panelists? Don't hesitate.
Just to support what Beatriz has said, I think one of the objectives of this FLAY AI group is really to create this community of practitioners and to get everybody on more work sharing information, especially in ATM, that at the end of the day is not such a big sector. So we all need to share what we are doing and learn from each other.
Thank you. There was a question going into the same direction. Is there a standard cycle one can follow or refer to on the process or consideration to be made in moving R&D on artificial intelligence from research to operations? And maybe that would be also interesting to know what is the work on EuroK 114 about this.
Yeah, indeed. So the standard will give a means of compliance to show how a use case in AI defined and implemented by industry and by maybe even INSPs or other organizations can work properly. So I would say that actually the different questions that you need to answer between going from an implementation, from an MVP towards a real product into practice. In the case of AI, are very much related to, I would say, to data first of all, because well, what is new here are the neural networks, and the data are very important for the specification of the algorithm. So first of all, in the standard and when you implement, so in the process you implement, you need to follow a very strict path in order to check the properties of the collected data, as Zoltan explained, but also at the system level, you need to pay attention into how you introduce this data. Other questions when you try to follow this path for checking if an MVP can be put into practice, and if you want to follow the standard recommendations, are related to the robustness of the machine learning models, therefore to the verification requirements. And of course, the first question in this case is to know if a model, how variable is a model with respect to the underlying training data set, how much of its characteristics will vary depending on the way it was trained, how robust it will be over time once in production to the variations into its input. And this variability into inputs was first highlighted by kind of adversarial attacks, but actually this can be completely unintended, and it is related to small variation in the input, like invisible noise, that will lead to unexpected behaviors of the model output. So the role of the standard will be to give guidance on how to detect adversarial input, how to detect unintended outputs of the neural network, and we shall need to be able, so any process of this kind needs to be able to assess through formal methods or through empirical procedures the robustness and of the trained models. But you can also check that you included in the training methodologies some methods guaranteeing the robustness of the model you will output. And last but not least, I would say that in the process and in the standard, you should be able to define safety mitigation in the system. If these training methods, if these assessing methods are not enough to guarantee all the properties that you would like. So this is a long process, and I would say this is why all the people involved in the standardization are so enthusiastic about working on it and trying to solve it and giving guidance on how to move on to bringing AI into into products, ATC products.
I just add a little bit to what Trace says. So now, most likely, the certification or the standard or the safety, the components that are the enablers will provide some help and there's some guidance. But I think just like in the industry overall, application of AI in aviation will depend. So the amount of time, the amount of work that's required to go from one phase to another phase, let's say from training to validation and from validation for deployment in production environment, would depend the application area. If you are deploying a machine learning for a very safety critical mission, then you would have to spend a lot more time testing and validating the output. If you are just automating some repetitive tasks, maybe you can be a little lenient and then not necessarily very conservative. So although the certification when it happens, or the standard when it happens, provide guidance, I think the extent to which you apply, how much time you need to spend from one phase to another, it's just a function of the area of application as well.
I think also what I would like to add here is, it's really important, as you said already, to understand the use case in the overall business process, so that you can integrate it well in the overall process and workflows. And then I think, as you said, it really depends then what effort is it for the next steps. But I think we should not forget the baseline in the beginning to really understand where you want to integrate it, which informations you need, and so on.
Thank you. I think it's time to move maybe to the human-machine collaboration questions, because there are a number of questions about this. Trying to find the first question on this. So first question was, will AI increase or decrease ATC controller workload, and what will be the role of the current ATC controllers in the entire control loop? And I will also extend this these questions to how far in terms of automation can we go in terms of with artificial intelligence.
Okay, so maybe I will take this question first, but I'm sure everybody has a lot of things to say. So for the example of conflict resolution, well, what AI can bring actually is speeding computation for the resolution, and also the possibility to take into account both the controller's experience and infinitely more alternative solutions. And in addition, to take into account other objectives like the green aspect, so the CO2, the noise, and also the airport and sector's capacity, the delays, and so on. So a lot of objectives into the global optimization. And for the human-machine collaboration, the goal is really not to replace the controller, but to free for him the time he needs to spend on all these routine tasks in order to allow him to focus on more critical solutions to the situations that really requires his contribution. And in this way, he has more time to think about this and to contribute effectively to the safety of the flight. So, another question was how this becomes more safe. I think you asked. This was the second question. Can you? So.
Yes.
Yeah.
Okay.
It was so the idea to integrate this these advisories into a safe architecture is the main the main reason why we contribute to the standard. But in the meantime, I would say for the moment, in the way to the automation. So as I have shown the standardization and the EASA roadmap for these more autonomous systems starting with 2024. But we don't know exactly how what will be the exact trade-off between the controller and the machine. So we think that the controller will use this time that is freed by the machine in order to handle more complex and unseen situations. But this collaboration with the machine needs to be refined during the user sessions with our customers. And in the meantime, we shall also increase and strengthen our contribution to the standard in order to have all the guarantees of the safe introduction of AI into ATM products. This would be my answer.
May I add something? It's just that's why I said that we have to understand our functional system, because in my opinion, it's not yet decided what will be the role of the controller. So it should be shaped now, and it should be shaped in local and global level.
Thank you. A lot of work to do still in this area, I think. If there is no other comment on this question, there is an additional question more or less on the same topic. What about safe transition of the human-machine system to degraded modes? And it makes the bridge to safety also. How the human can recover from degraded modes if AI is having safety issues or problems or limitations.
So I think one aspect here is that the AI should, or the machine learning component should handle also abnormal and non-nominal situation. And another important aspect is integrity, so that the component let the air traffic controller or the operator know if there is some degradation in its performance. And I think it should be assessed, should be carefully assessed during the safety assessment before the machine learning component implementation, that how the component will interact, the model will interact with human, and what are the procedures for safe handling of degraded modes. So this is maybe one of the most important aspects of a safety case of a machine learning model and component.
I fully agree, and I would add that indeed one of the characteristics of the AI systems that we introduce needs to be this capacity to function and to provide answers with accompanied by the capacity to know if it functions in the nominal regime. Okay, so the AI system should be accompanied by a safety envelope, so the possibility to move towards a degraded mode if the answer is not in the range expected for this functioning. And well, in the systems we implement currently, we have, first of all, advisories or increased awareness. So you provide more information, more precise information to the end user, to the ATO. And in this case, you can give the limit, different probability information about the measure that is provided. And in case of advisories, we keep the human in the loop. So this is also a way for the human to accept or not accept the advisory in case something seems not normal to him. And overall, there is also a system aspect because the whole AI module is included into a safety architecture that manages this degraded node.
Right. Just a few addition. Now, just like any other software system, I guess the extent to which how you monitor the system, and then when you know what is the trigger point where the performance system has degraded that, and then you have to take over, depends on the application area. But I think it would involve some kind of independent monitoring, so the AI will have to provide some self-reporting of its performance and has to be monitored by an independent system to continuously probe the AI and to determine its health level. And when it is determined that this has fallen below some threshold, then it's time to trigger. I think the implementation detail could be different, but it has to involve some kind of monitoring of its performance through an independent means.
Thank you. This leads to one of the questions that I think is a bit provocative. In the case of AI-driven machine, is the human not now the risk in terms of safety? I mean, if it means if the human is no more in the loop or gets out of the loop, doesn't he become the risk?
Right, so I think we highlighted this in the paper, and so at least for the near-term application, we don't envision AI to fully replace human beings. It's going to be a collaborative environment where the machine will rely on things that needs to be scalable, not where humans are not good at. And then still the critical decision making has to be supplemented by humans. So again, the near-term application is most likely is going to be a collaborative environment. So there's no room for just AI to operate by itself. Now, I'm sure the technology at some point will mature enough that we don't need humans in the loop at all, but that is where I head in the future.
Yes, thank you. And that's also my view. Maybe a question about voice recognition, speech recognition. When using speech recognition for command and control, was there a concept to segregate vocal intervention to manage the traffic from those to command and control the system? Do you see the issue?
I think for command and control, clearly what we have seen is we are concentrating how to integrate it into the overall user interface and workflows. So one thing is the form fill in. Command and control is sometimes quite difficult to integrate because really speech controlling, has some impacts because you're also using the voice for communication with the pilot and so on. So therefore the concept of speech recognition is more as assistance, taking the voice or taking the commands what you are speaking, for example, to the controller, and then doing something with it in the user interface. But I think that the concept of command and control directly, as you know it, for example, in aircraft, also in the fighter aircraft or whatever, or in the car navigation, I think this is a concept which is not so applicable in ATM.
Okay, thank you. I think we are coming close to the end, and I will close the question session. So if you can move to the next slide, Hélène, for the closing slide. So just this slide to remind you that this artificial intelligence white paper will be published very soon in this month, and we look forward that you download it from the Kanso website. So now I'd like to, next slide please, just to introduce the next Fly AI webinars in the name of Eurocontrol. So the next Fly AI webinars will be on the 28th of April, and its topic will be AI trustworthiness guidance, paving the way to safety-related AI certification, and it will be moderated by EASA. So that's the end of this webinar. I thank you very much for your participation, for your attendance, for the question. The questions that we have not been able to answer will be answered directly. I think the names were taken. And I also encourage you to follow our next Kanso white papers that will come and will be published in the coming months. Thank you very much. Goodbye.
Thank you, Patrick, and thank you to all our speakers today, and a great big thank you to everyone for attending. Once you leave today's webinar, you will receive a survey, and we would appreciate if you would complete that and provide any feedback. So on behalf of CANSO and Eurocontrol, thank you for joining us today and enjoy the rest of your day.